Hello. So, we've seen that local extrema could be very useful. We've talked about a couple examples and how to find local extrema. But sometimes, right, you just want the best of the best. You want the sort of ideal solution. You want the maximum, right, as opposed to just a local maximum. So these things are called absolute extrema. Now, absolute extrema are found pretty much the exact same way as local extrema, almost, right, with a little asterisk. So looking at absolute extrema, most of the time, sort of in practice, for most applications, absolute extrema are simply the local extrema that are exactly that, the best of the best, right? So it's the largest maximum or the lowest minimum, right? So to find those in those cases, then it's basically the same system. You find the absolute extrema simply by going and finding all the local extrema, finding what their values are, and then picking out exactly those, right, highest or lowest points. But there are two exceptions. So that's pretty much what we're covering in this video. So keep in mind, right, that generally speaking, this is sort of the outline to start with, but there's sort of a couple extra steps when you're worried about absolute extrema. So the first exception, determine if there are absolute extrema. This is sort of the easiest one to overlook because people sort of jump straight to looking for the local extrema and running down the rabbit hole. And there could have been sort of way less work involved if they had bothered to check if there was going to be absolute extrema. So basically, the first step of actually looking for absolute extrema is to determine if they're there. So to determine if you have them, we need to know what the range of the function is, right? So the whole idea of an absolute extrema is that it's the highest value attained or the lowest value attained. So if we know if the function goes, say, to infinity or negative infinity, then we know it wouldn't have, right, a highest or lowest, respectively, value. So to know that, right, we want to go figure out sort of the two ways that we know functions can go off to infinity. So we know that it can do that as part of that n-term behavior. So that means that we want to look for horizontal asymptotes, or sort of that exactly n-term behavior bit, how it's occurring as we go sort of infinitely far out. Again, in both directions, right? Because we've seen that functions can behave differently in either direction. And we want to look for vertical asymptotes, right? Because vertical asymptotes, again, as we've seen, many examples where it sort of can just have them go off to positive or negative infinity in some small area by having one of those vertical asymptotes. Okay, so on the other hand, if we have something like a bounded domain, right? So if we're looking at a function and we only care about some sort of small part of that domain, like interval a to b, then we don't really have to worry about n-term behavior because we're not actually going to that n-term, right? So we never actually have to worry about sort of going far away because we're staying within that interval. So it turns out, as sort of an important and useful side note here, that if the interval is closed and the function is continuous on that interval, then we actually immediately know it has to have absolute extremas. This is the extreme value theorem, which we'll do in another video. But just as a quick note, right, if you do have this situation where you know that you have an interval that you're considering, it's closed and it's continuous, you've already determined that there are absolute extrema without actually doing any work at all. All right, so if we don't have any vertical asymptotes, right, if we do, then we have to know sort of the sign that it's going. If they're both going, say, positive infinity, then we know that it might have a minimum, but if one's going positive and one's going negative, that kills both possibilities, right? We don't have any absolute, and if they're both going to negative infinity right on either side, then we might have a positive, a higher point, right? So a maximum, absolute maximum. If we don't have a vertical asymptote, and we can determine either that the horizontal asymptotes are finite, right? It sort of stabilizes at some finite y value as it goes infinitely far out, or if the domain is bounded, meaning we don't really have any of this n-term behavior, then we can go ahead and find the actual absolute extrema, right? So basically, if we know that we don't have an infinite sort of y value, right? If we're not going to positive infinity or negative infinity, then anywhere, then we can tell that we're going to have absolute extrema. We can start the hunt. All right. Exception 2, right? So start the hunt. You start by finding the local extrema, get all the local extrema, and you try to sort of keep going. But we mentioned earlier, right, if you're on a closed interval under certain conditions, you know that there are absolute extrema, but it turns out being on a closed interval is sort of a blessing and a curse. So if you're on a closed interval, this falls into the second exception, which tells us that there's actual additional stuff we have to check. So if we're on this closed interval, specifically, we need to test the endpoints of that interval. So to see why, it's actually just sort of easier to look at an example. So let's consider, for example, f of x is x squared minus 4. This is a sort of standard parabola moved down 4. But we're only going to look at it on the interval -3 to 1. So we have something that looks like this. Now, if I sort of ignore the interval for a second, right? Or maybe I should say, like, I go through my exception 1 sort of thing, and I'm like, okay, I need to worry about horizontal and vertical sort of asymptotes and behaviors and that kind of thing. I look at this, it's defined everywhere. There's no sort of domain restriction, so I don't have to worry about vertical asymptotes. And lucky me, I'm on a closed bounded interval here, this -3 to 1, so I can be like, I don't have to worry about end-term behavior, so I know there's going to be a maximum and minimum. Moving on. So I'm like, okay, so take the derivative, right? Find my local extrema. So I take the derivative, I get 2x. Well, that tells me that there's a critical point at 0, I can test 0, and indeed I'm going to find local minimum, right? 0, -4. But wait, I claimed that there should be a maximum and minimum. I've only found one critical point. So like, even if I'm like, well, maybe it was a maximum and I messed up the math, I only have 1 point. I can't have both a max and a min with only one value, right? At least not with a curve that isn't flat. So clearly I must be missing something. And the thing that I sort of forgot in this process, or haven't accounted for yet, is the interval, that -3 to 1. Because just looking at the derivative isn't really thinking about the interval. The derivative is thinking about the whole function. And if I think about what the full function looks like, it's this big parabola. So there's no reason for me to even think about what might happen at these endpoints, right? Because the derivative is thinking about the full function and not these endpoints. Those endpoints are exactly where those potential maximums are, right? Because if I go back a step here, looking at these endpoints, all right, this is going to be the highest point I attain, so this is going to be an absolute maximum, and this is sort of some kind of local maximum, depending on who you ask, which I'm not going to get into the weeds there, but it is some sort of truncated point that could have been an absolute maximum depending on the value of the other one, right? So I have to account for these by testing those endpoints because the derivative is thinking about this as the full parabola and doesn't return those as a critical point. So whenever you have a closed endpoint, you sort of always have to test that endpoint because it's not going to show up as a critical point. Because from the derivative standpoint, there's no reason to think it should be a critical point because it thinks that the derivative keeps going, right? That the function keeps going through that value, and it wouldn't be a maximum or a minimum in that case. So you sort of have to independently test these things. As a side note, this is only true if you have a closed endpoint, right? If I had open -3 to open 1, then I wouldn't test those because sort of by definition, those values aren't included in the domain, right? So if they were open endpoints, I actually wouldn't have a maximum, even though it's sort of bounded. This gets into a weird sort of side effect, but in practice, this doesn't usually occur. Usually, sort of in the real world, we have very definite ending points. It doesn't sort of vaguely trail off in some finite sense when you're dealing with basically anything in reality. So it's very rare to sort of run into that distinction. Nonetheless, it is an important one to sort of keep in track, sort of keep in the back of your head as we're moving forward. All right, so what do we do? So process of finding absolute extrema is essentially the same as finding local extrema, with a couple exceptions, right? So you need to check these two things. First, you have to know if there are absolute extrema, because it's possible there aren't. So this is typically done by looking for the vertical asymptotes and the horizontal asymptotes. But really what we're looking for is to see what the range is, or more accurately, whether we're going to positive infinity somewhere and negative infinity somewhere within the range, right, within the domain that we care about, because that would be sort of canceling out the max or min, sort of respectively. If you've done that part and you're moving forward, then if your function is defined on some closed interval or has some closed endpoint in the interval that we're looking at, you need to check those endpoints as well, because they don't show up as critical points, because they aren't critical points from the derivative standpoint. This is sort of an artificial thing about your domain that's getting pushed onto the problem. So you have to check them independently of everything else. Okay? So that is that.